Okay, back at it here. Should have mentioned the last time that as you're going through these, you probably want to write some of this down so that it makes sense as we go through. We're going to have to try to figure out how basic circuits look when you draw them together. You've probably seen pictures of circuitry from certain devices. Let's see if we can make some sense of this. If you have a straight line, that represents just a wire in the circuit. If you have a wire connected to two parallel lines, one long, one short, that represents a power supply. Thing to understand is that the short lead is the negative and the long lead would be the positive for the power supply. Next, if you have a zigzag line, that's going to represent what we call a resistor. You have two poles that you touch one to the other. We refer to that as a switch. And two devices they use to measure different things. If you have a circle with an A, that's representing a device called an ammeter they use to measure current. And a circle with a V represents a device used to measure voltage, which we call a voltmeter. Okay. So when we look at different types of circuits, or at least just looking at the most basic circuit we could come up with, appears as though you have a power supply and connected to that is a resistor. Connected to that would be an ammeter and then another wire back to the power supply. Right now we're going to say the total voltage of this power supply giving us 10 volts and the resistance of that resistor being 100 ohms. Things to define. The current is usually what we refer to as the positive charge flow. Even though maybe in the last unit we always talked about the electrons going in a circuit, moving throughout a wire, we're going to call this the positive charge flow, measured in amps. So it's going to flow from positive to negative. Notice that the current will flow through a resistor. And that's why you're putting the ammeter the way you are, because it's then going to flow through the ammeter. If we had time and we had the ability, which we don't have possibly, to go through a lot of these labs in class, we might have to do it electronically, is that it does not matter where we place this ammeter, we're going to get the same amount because there's nowhere else for this charge to flow. It goes through the resistor, through the ammeter, and back to the power supply. There's only one pathway. Therefore, wherever you would happen to place this ammeter, which over here I could put an ammeter, I would get the same answer for the current in either spot, before or after that resistor. So the current flows through the resistor. Voltage is said to be established across a resistor. Well, what does that mean? Well, that means that if you put a voltmeter, you would place that voltmeter right there. That would measure the voltage or the energy used by that resistor. So it's a measure of how much energy that resistor used. But you have to place it in that position to measure that. Okay? One other thing I want to mention about this is there is a law called Ohm's law that tells you that there's a combination or a connection between the three variables, and that is the voltage is the current multiplied by the resistance. And so in this particular case, if I wanted to know what that ammeter would read, I could manipulate that equation and say the current I would read is the voltage over the resistance. Well, the voltage, there's only one place for the energy to be used up, and that's at the resistor. So that resistor is going to get the total of 10 volts. And the resistance is said to be 100 ohms. So what I'm going to get is 1/10 of an amp measured by that ammeter through that resistor. Next thing is there are different types of circuits that we have. This one is called a series circuit, and that is that it has 3 resistors piggybacked one to each other. Again, the positive current flow comes from the positive lead. And notice that there's nowhere for it to go but straight through R1, and once it goes through R1, it's going to go through R2, and then it's going to go through R3. And the idea is that it's going to stay the same since there's only one pathway. The total amount of current that comes out of that power supply is going to be the same as what it is for the first resistor or the second or the third. Therefore, if you put an ammeter anywhere, it would read the same. So the current is the same in a series circuit. Okay? But each resistor is going to use up energy a little bit different. So if I put a voltmeter here or here, if those resistances aren't the same, then they're going to use up different amounts of voltage. The voltage at the first resistor would be that current times the resistance. The voltage in the second resistor would be that total current times the second resistance, and so on and so forth. What you find is each one of the resistors is going to use up some of the energy. So the total energy used up is additive. So it would be like voltage 1 plus voltage 2 plus voltage 3 gives you the total voltage. And what we want you to realize is that if you put in that each one has the same current times the same individual resistance, an interesting thing pops out is that the current is the same, and it gives us an equation for what we refer to as the total resistance, or sometimes known as the equivalent resistance of a circuit. For series, it is just additive amongst all those resistors. It's the same for each one. Okay? So those are the kind of things that you need to know about a series circuit. The next type of circuit we're interested in would be a parallel circuit. This is an example of one where you have R1, R2, and R3, but they're hooked up in parallel. They're said to be hooked up individually across power supply. So I'm going to symbolize power supply by the PS. So what that means is they each get the total amount of voltage. So in the last circuit we said that the current was the same in each. Here we're going to say the voltage is the same in each one of those. But the current is not the same. The current that comes out of the power supply has different ways. It can either go through this resistor, go through the second, or go through the third. Well, it turns out then, in that case, that the total amount of current in each branch would add up to the total amount of current throughout. So we might say here that if you put a voltmeter, that would be the same. But the ammeter measurements are all going to be different. And the thing to write down about that was we could substitute using Ohm's law and get another equation for resistance for this type of circuit. And so if you follow along with me, I'm going to put in V over R for each one of those individually. So V01 over R1 plus V2 over R2 plus V3 over R3. And realize that the voltage would be the same, so it kind of cancels. The total resistance in a parallel circuit, which we also call the equivalent resistance, would just be what we refer to as reciprocal additive. It's not quite as easy as adding them together, but it's the 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. And the other thing is that the current is additive. Okay? We would all learn this in the lab. Again, it's not quite as easy given what we have, given not being in class. The last type that we have is a combination circuit, which kind of uses both of them. And we're going to say R1 is in series with the power supply, but then in parallel with both R2 and R3. So you're going to have some things about series and others in parallel. That R1 is going to get, if you said I1, that would equal the total. It's going to get the same as what's given out of the power supply. If you put that little dot there, it's also called a junction. When that current goes into that junction, it's going to have two pathways. It could either go through R2 or R3. So it turns out that I1 is going to equal I2 plus I3. There is a rule for that. Depending on how you pronounce this gentleman's name, I was always taught that it was called Kirchhoff, a German name. Some pronounce it Kirchhoff. But he has a junction rule that says the sum of the currents going into a junction equals the sum of the currents coming out of the junction. So the current coming in is I1. The current going out, that is a 1, equals I2 plus I3, which would be the current through R2 and R3. This is also another way what you would call the conservation of charge. Okay. The other rule is called the loop rule, Kirchhoff's loop rule, which says that the sum of the voltage drops around a pathway is equal to 0. And what that means is there are two different ways that charge can flow, either around this loop on the inside or all the way on the outside. Those two are essentially the same, and that's just a restatement of the conservation of energy, because it's telling you how much energy is used up as you go through a path. You gain energy when you go through a power supply. You lose energy at a resistor or another resistor. But you happen to know that the voltage drop on R2 and R3 have to be equal because those two are in parallel. So you use a little bit about series and parallel. That'll be it for now. We'll talk later. Be safe.